Hey students, welcome back. This is Unit 5. This is kinetics, all right? So we are talking about kinetics, which I don't believe you've probably had a lot of background on. So please make sure you do the background vocab. And remember that you can find more information about kinetics right here in 15.2. You could read about 15, you could read 15.1 as well. There's a little story about a lizard in there. It's actually kind of cool and also kind of cruel. So, yeah. So let's jump into kinetics. Kinetics is the rate of a reaction, or how fast a reaction goes. All right, so we're talking about the speed of a reaction. And there are times that we want to speed up a reaction. There are times we want to slow a reaction down. For instance, we don't want our food to go bad a lot, so we want to slow that reaction down. That's why we actually put it in the fridge, because most processes are sped up when they're warmer, right? So we'll actually talk about the why of that later in this unit, but let's jump into kind of the background information, and let's start with reaction rates. Reaction rates are just basically the measuring the speed of the reaction. All right, so we're talking about how fast the reaction goes. So what is our speed of the reaction? So it compares to how we calculate the speed of a car. If I took a trip and I traveled 300 miles and it took me 5 hours, I would have been traveling at an average of 60 miles per hour, right? So as we're driving a car, we take total distance divided by total time, right? That's how we find speed of a car. All right. Now we could do that same thing, except in a reaction, we're probably talking about changes in concentration. And what we know so far for our change in concentration, remember delta, the delta sign means change. So we're talking about a change in concentration, and I'm just going to arbitrarily use A. All right. That's just a chosen one. So the change in the concentration of A over our change in time, and that would be how we calculate our rate of reaction. So very simply, it's very similar to calculating the rate of a car. So now as we look through this, we have a reaction here. We have aluminum and oxygen forming aluminum oxide. If we think about the reaction, as the reaction goes forward, aluminum and oxygen are both getting used up, and then aluminum oxide is being formed. So if we're trying to compare rates exactly, right, we're going to, in front of our reactants, we're going to put a negative sign, because that will give us a positive rate, and that just makes sense to do. So we're going to say the negative change in aluminum concentration over the change in time. That would be for aluminum. Then we do the same thing for oxygen. Negative change in the concentration of oxygen, and I should put O2 there, over our change in time. That'll tell us our reactants, and remember the products are being formed, so that's going to be a positive rate, right? Our final minus our initial. And so that we're just going to say our change in our concentration of Al2O3 over our change in time. Now, relating these together, we have to go to our stoichiometry, all right? Because for the 4 aluminums that I use, I only use up 3 oxygens, so they can be related based on their stoichiometry. So for this to compare all together, we would say negative 1 over 4, and then our change in our concentration of Al over our change in time is equal to negative 1 over 3, because of our balanced chemical equation, the 3 there, change in the concentration of O2 over our change in time. And then that's going to be equal to, yes, you guessed it, 1 over 2, change in the concentration of aluminum oxide over our change in time. And that's how they would relate together, because for every 4 aluminums I use up, I'm forming 2. So I have to use 2 aluminums for every 1 aluminum oxide I form. All right, and that's how they relate. This kind of goes back to what we just talked about. Notice how our reactants are decreasing. Reactants are decreasing over time, and our products are increasing over time, thus that negative rate. So let's see if we can't put this together and do ourselves a nice little example here. So we have this reaction here. We have H2, we have That's hydrogen peroxide, plus 3 I's plus 2 H pluses gives us I3 minus and 2 H2O I's. Now remember, this is a net ionic equation, so we don't always see everything, but in this one we've got what we've got here. So what we've got is it says in the first 10 seconds of the reaction, the concentration of I minus drops from 1 to 0.868 molar. And then it wants us to calculate the average rate of this reaction at that time. So if we look at our balanced chemical equation, we know that our rate in terms of I minus is equal to negative 1 over 3. That 3 right there, it should change in the I minus over our change in time. So we just kind of can plug in that information that is given to us, negative 1/3, right? And then we have our 0.868, final minus initial, 0.868 minus 1, over our change in time, which was 10 seconds. And this would give us 4.40 times 10 to the negative third molar per second. All right. So some things that maybe I didn't hit earlier, but I want to make sure we focus. When we're talking about change in anything, that is final minus initial. So we're talking about final minus initial every time. So this was our final and this was our initial in this case. Okay. Now we're also supposed to compare that to our H plus. Well, we know that, if we look at our rate of H plus, if we write it out, it's rate of negative 1 over 1/2, right? And then our change in H plus over our change in time. So we're solving for this right here. And so we already know our rate, which was here, so we'll just plug that in. So we have 4.40 times 10 to the negative third, and then let's look at it all together, 1/2, and then we have what that we're looking for. All right, so to isolate this, we need to multiply by negative 1/2 on each side, right? Negative 2 over 1, right? Take that to the other side. And we should get negative 8.80 times 10 to the negative third molarity per second. All right. Okay, awesome. Now, how do we measure rates of reaction? How do we measure rates of reaction? Well, there are a couple of ways we can do it. These last two are the major ones and the ones that we might use in class. We'll definitely use the spectroscopy one. We might not use pressure measurement, but we'll see. But polarimetry, whatever, measures the polarizability of a substance. So basically, you just measure how well it polarizes. And this is really more to do with organic chem, all right? Because in organic chem, you have left-handedness and right-handedness, cis and trans isomers. So you have isomers, and they talk about polarizability in there. So this would come more into your organic. So this would probably be your second year chem class versus this first one. Okay, to use spectroscopy, all we do here is we just measure color change, right, over time. If you remember our spectroscopy, we're talking about colors changing, right? We measure the color, and so we can do that. That's actually going to be our first lab. All right. Then we have pressure measurement. Again, if we have different amounts of solids and liquids and gases in a chemical reaction, we can just measure the change of pressure throughout. All right, so pretty easy to kind of use these and figure these out. All right. Okay, see you next video.